Okay, welcome back. In the last class we discussed about the manipulator, the Jacobian, and how the Jacobian can be calculated, as well as some of the issues associated with the use of Jacobian, like the singularity issues as well as the inverse of Jacobian. And then we found that the singularity can be identified by looking at the dexterity, which can be calculated using the Jacobian, and the inverse Jacobian, when the matrix is non-singular, we can use a pseudo inverse to get the inverse and then solve the inverse problem and get the velocities. And we saw the method of using resolved motion rate control for robots, where we use the pseudo inverse to get the velocities q dot or the joint trajectory using the Cartesian velocity details. So, this was what we discussed in the last class. Now, this Jacobian what we have can be used for many other applications also. If not only for the velocity relationship, we can use it for force analysis, etc. And in order to make it suitable for that analysis, we actually what we do is we define this Jacobian. So, the previous Jacobian what we discussed, we normally mentioned it as tool configuration Jacobian, because we were trying to relate the tool velocity to the joint velocity. So, in order to look at the Jacobian in a slightly different way, we define the Jacobian in this format. Suppose you have these joints and this is the tool configuration. So, whenever we have a displacement theta k, we know that there is a displacement d phi, or the change in the position and orientation of the tool. So, we assume that there is an infinitesimal displacement of dq at the joint that will lead to an infinitesimal displacement of du at the tool displacement. And for the given operating point q, at the particular operating point q, this Jacobian can be defined as a relation between this du and dq. That is, an infinitesimal displacement of displacement at the joint leads to an infinitesimal displacement at the tool tip, or any infinitesimal displacement at the tool tip leads to an infinitesimal displacement at the operating point at the joint. And for any given operating point, that is any given current configuration of the manipulator, you will see that you can relate this infinitesimal displacement with a matrix, and that matrix is the manipulator Jacobian. So, in a way it is the same as the tool configuration Jacobian also. What we are trying to say is that we are not really talking about the velocities per se here. We are saying that a very minor displacement can be related using this jq. Though our normal displacement q and x are related using the forward kinematics, here we are telling that very small displacement can be related through the jq, and this jq, the Jacobian, the manipulator Jacobian, can be used to represent this relationship. So, that is the way how the manipulator Jacobian is defined. So, now once you have this relationship, we can actually relate the displacement, and therefore, we will be able to use it for the static analysis also. So, how much it is can deflect if I apply a force here, or there can be a displacement at this point, and that may lead to some displacement here, and that can actually be used for finding out the relationship, the static relationship. So, that is the way how we can use the manipulator Jacobian. Okay. So, it is only a slight difference in the way we define it, but otherwise the concept remains same. They are actually the relationship between the displacement at the tool tip and the joints, but here it was we are considering it as a very minute displacement. So, instead of velocity we are saying a small displacement at a very short interval. So, with this definition we will try to now calculate the manipulator Jacobian. Okay. So, the principle is the same. What we do, the manipulator, the Jacobian can actually be defined as the linear and velocity parts. So, you have the jq, the Jacobian, as the aq and bq two part, we divide them into two parts. The first one is associated with the linear tool displacement, and the second one is the angular displacement. So, a and b. So, in a way we can say dp, which is the displacement, the positional displacement at the tool tip, can be defined as aq dq, and the d phi, the minute displacement, I mean the angular displacement is given as bq dq, where dq is the joint displacement and d phi is the p and d phi are the tool displacement. So, this way if you define the Jacobian, now we can calculate A and B and then find out the complete Jacobian of the manipulator. So, A for the linear tool displacement and B is for the angular tool displacement. Now, AKJ, as we saw in the previous examples also, the AKJ is basically the partial derivative of P with Q, that is the position change in position with respect to the joint variables is the AKJQ, that is the top part. So, you have the Jacobian and the top 3 for the linear velocities. So, the linear velocity part is actually obtained by taking the position with respect to Q, the partial derivative of position vector with respect to Q is the AKJ, that is the elements of the linear part. Now, we have the angular part. So, what is the angular velocity or what is the relation for angular velocity component of the Jacobian is this lower part B. Now, this B can be obtained. So, B can be obtained as the kth column of BQ, that is the kth column. So, this is kth is equal to 1, 2, 3 etc. The kth column is obtained as BQ is small bkq, small bkq is given as a constant xi zk minus 1 q. Okay, that is the way how this bk is defined. So, this bk is a vector, it is a vector and then that is defined as xi is a constant, it is a 0 if it is prismatic, 1 if it is rotary. So, that is xi parameter here and then zk minus 1. So, zk minus 1 is the rotational axis of the k minus 1 joint. So, zk minus 1 is the rotational axis of the k minus 1 joint, or we can say that zk minus 1 is r0 k minus 1 I3, right. I3 is the identity vector or 1 0 0. So, you can actually multiply I3 0 0 1. So, this is the third unit vector. So, I3 multiply r0 k minus 1 I3. So, this is the zk minus 1. So, the top part which is the linear velocity part, that is obtained directly by taking the partial derivative. So, if you have the forward relationship T tool to base, then you get Px, Py, Pz and then you will be able to get the partial derivative. But for each column you have to take 1 0 2 0 etc. and then get the partial derivative. He will be getting the partial derivative and getting the velocity relationship here. Then that is Px with respect to q1, Px with respect to q2 etc. you will be taking and then getting the relationship. Then for the angular velocity part we will find out this bkq. So, this is given as bkq, bq is bkq, that is the vector b1, b2, b3, b4, that is the way how it comes. So, the b1 q will be z xi z0, that is what is the joint axis vector of the first frame, that is the z0 coming here. And if it is rotary it will be 1, if it is prismatic then there is no rotation and it is 0 and there is no rotation and there is no angular velocity, therefore, this bk will be 0. So, for whenever there is a linear joint or a prismatic joint, it has no contribution in the angular velocity of the tool tip, that is what it says. So, if you look at this once again from the manipulator point of view, suppose you have the manipulator like this. So, this is the manipulator. Now, it says that the linear velocity part how the position is changing with respect to q1, q2, q3, I mean the joint variable. So, you take this Px and then find out, suppose this is q1, what is the relation of Px with respect to q1. So, how the Px changes with respect to q1 is obtained by taking the Px over q1, that is what you can get. Now, the next question is, when this q1 is moving, when this is theta 1 or q1, when this is rotating, what will be the angular velocity of this? That is what actually we are trying to find out. And it says that if this is rotating and the change in angular velocity will be as per this axis. What is this axis? And that will be the way how it is changing. If it is with respect to z axis, the orientation will be changing with respect to that. If this has a different axis with respect to the origin, then there will be a different way it is changing. That is why it says that the orientation, the first vector, the change of orientation with respect to the first one will be 0 0 1, because the axis is aligned like this, the z axis is 0 0 1, and therefore the orientation changes will be also like that. So, the orientation will change as this changes, the orientation will change with respect to this relationship. Okay, that is what actually it says. Similarly, the second one, how this joint axis is aligned with this, accordingly whenever this rotation happens here, the rotation of the angular velocity at this point will be related to the orientation of this axis with respect to the base frame. So, we will try to find out what is the orientation of this axis with respect to this frame, and that will be given as the second one here, the Z2. The B2 will be the second joint axis. So, the second joint axis will be this one, and this will be the nth joint axis or n minus 1 the nth axis, what will be with respect to the base frame. So, this is the way how you get the Bk for the manipulator. So, it will be more clear when we take an example, but what we are trying to do is to get the first part, no issues with the linear part. The lower parts, if it is a rotary joint, prismatic joint, a prismatic joint is not going to change the orientation of the tool, and therefore this Bk will be 0. If it is prismatic, this will be 0, but if it is rotary joint, then the rotation of that joint axis, the rotation of the joint with respect to that axis will lead to a change in the orientation of the tool tip. So, the orientation of this axis is the one which actually determine the change of orientation at the tool tip. So, this Bk will be the orientation of this axis with respect to the base frame. So, that is what we are getting here. So, by doing this multiplication, we are trying to find out the we are doing this Zk minus 1 is basically the joint axis. What is the joint axis? And that joint axis orientation can be obtained by from the rotation matrix that we have. So, we take the rotation matrix 0 k minus 1 and multiply with I3, you will be getting the vector which is the Zk minus 1. So, basically that is the z axis of the k minus 1 joint. So, this is the way how we get the manipulator or compute the manipulator Jacobian. I hope you got it. So, to explain it once again, so the Bk, the kth column of B or the Bk is given as Bkq is xi Zk minus 1 q, and Zk minus 1 is xi is 0 if it is prismatic, 1 if it is rotary, and if the Zk minus 1 can be obtained by taking the rotation matrix 0 to k minus 1. So, 0 to k minus 1 rotational axis we will take and multiply with I3, the unit vector in the third axis, and you will be getting the Zk minus 1, and this is 1 less than equal to k less than or equal to n. So, you will be getting Jq like this. The top part is the angular linear velocity part, and bottom one is the angular velocity part Bq. So, this is the way how we get the complete Jacobian matrix. So, in the previous examples we did not consider this. So, now we are considering the full Jacobian matrix for both linear and angular velocity. Okay, so, the algorithm is like this. So, set T0 0 is equal to I, that is the transformation matrix T 0 0, that is there is no 0 axis to 0 axis, 0 frame to 0 frame, the identity matrix. Then compute Bkq, that is now k is equal to 1. So, set k is equal to 1. So, I have B1 is xi k, that is I1, xi1 r 0 0, k is equal to 1 and multiplied by I3. Okay, that is B1. So, B1 is xi1 r 0 0, xi1 is equal to 1 when it is rotary, 0 if it is prismatic. So, if it is a rotary joint, then B1 will be I 0 0 is 0 0 is the rotation matrix between 0th frame to 0th frame, it will be always an identity matrix. So, it will be 1 0 0 0 1 0 0 0 1 multiplied by 0 0 1. So, what we will be getting is 0 0 1. So, BK, so B1 will be 0 0 1, basically says that the joint axis is aligned with the z axis and the first z axis. So, it will be 0 0 1. So, that is BK will be 0 0 1, B1 will be 0 0 1, and then compute T0K, that is next is T0 1. So, you calculate T0 1, okay, and find out what is T0 1. So, that you can actually get from the transformation matrix between first and 0th frames, 0th frame to first frame, what is the transformation can be obtained T0 1. Now, set k is equal to 2, say k is equal to 2, then find out. So, now k is equal to 2, then go to B2, B2, and B2 will be again you will get this is I2 R0 1. So, this will be, if it is rotary joint, it will be 1 R0 to 1 I3. R0 to 1 I3 is R3, R0 to 1 will be a rotation matrix, which will tell you what is the how the z axis of the first frame aligned with respect to the base frame 0, and you will be getting this as again a vector here, that may be sin alpha cos alpha 0 or something like that, depending on how the axis is aligned with the 0th frame. So, you will be getting this as the B2, and similarly you go for B3, B4 etc., and finally get this AK, that is the top part of the linear part, by taking the partial derivative and form the JQ. So, this is what actually we will do in the computation of Jacobian for the whole manipulator. Okay. So, we will take an example. So, it will be easy for you to follow how it is done. So, we will take the example of this 5 axis robot Rhino and see how the Jacobian can be obtained for this robot. Okay. So, we need to have the the transformation matrices calculated for all phi is equal to 1 to 5. So, we need to have the initially we need to calculate T0 0, okay, T0 0 and you need to calculate T0 1, T0 2, T0 3, T0 4 and T0 5 should be available. That what we need to calculate all these transformation matrices. So, normally we do not do this for forward kinematics, we do not need to do this 0 to 1, 0 to 2 etc. But we need to know now, because we are interested to know what is how the joint axis 2 is aligned with the 0 axis, or how the joint axis 4 is aligned with the joint axis 0, I mean the 0th axis. So, this information we need, and that is why we need to calculate these matrices T01, T02 etc. So, this is to be calculated first, all the transformation matrices from 0 to T0 to I. And then we have of course the T0 5 will give you the Px, Py, Pz, that is the position vector tooltip. Now, the B1Q, okay, so what will be, we have this B1, so we will be having AK and BK. So, you will be having A1, B1, A2, B2 etc. That will be the Jacobian. So, this B1 will calculate, B1 will be R00 I3. So, it will be always 001. So, this will be 001 if I take this as the Jacobian. So, this BK will be, B1 will be always I3, because the joint axis Z0, the first joint axis aligned with the base frame. So, it will be always 001, base frame Z axis, that is why the joint axis and base frame Z axis are aligned. So, you will be getting it as 001. Now, we will find out what is B2. Okay, so that one is written here. So, the first part, so we will get J1. J1 is the first column of the Jacobian, it is given as J1. So, the first column of the Jacobian you take the partial derivative of p x with respect to q1, you will be getting j1. So, this is first derivative, okay, p x over q1. So, this is obtained as p x q1 and py q1 and pz q1. So, pz is independent of theta 1, that is why you find it as 0 here, and you have the b1 as 0 0 1. Now, let us see the b2. So, we need to get b2. So, to get b2, what we need to do is 0 1, since it is a rotary joint, xi is equal to 1. So, 0 1 I3, that is what we need to find out. So, R01 basically is that from T01 you can get R01, and it says that how this joint axis or how this joint frame is aligned with this frame. So, now this is Z1 and this is Z0. So, how Z0 and Z1 are aligned is obtained from this one R01 I3. So, if you take R01, it says what is the orientation of this coordinate frame to this coordinate frame, and then we need to know what is the axis Z1, how is it related to the axis of the coordinate frame Z0, I mean the base coordinate frame, and that is obtained by getting this Z1. So, Z1 is obtained as like this. So, this is T01, so this is T01, and as you can see here, basically we are looking for this vector. So, this is the vector we are trying to get, this is basically the B1, and by doing this exercise, this multiplication, we are trying to extract this out. So, B1 is minus S1 C1 0, and that is why coming here is B2S, sorry B2S minus S1 C1 0. So, this is B2, sorry. So, B2 is minus S1 C1 0. I hope you got it. So, what we have to do is to get T01, and from T01 get R01 and then multiply R01 with I3, you will be getting this as minus S1 C1 0. So, once you are comfortable, you do not need to really do the multiplication, just look at the approach vector and take that approach vector and add it here. So, that approach vector will be the one which we will be using here. So, this is the way how you get the B2. The same will be repeated for B3, B4, B5. So, we will take T01, now take T02. So, take T02, so this is T0, from T02 you will be getting this as minus S1 0. So, you can see that this one is minus S1 C1 0, and this also next also will be minus S1 C1 0, because the orientation of Z2 is also the same Z1. So, it will be again the same way you will be getting it, because there is no change in orientation. So, you will be getting it as this way. So, that is the way how you will be getting it. Okay. So, then you will be moving to the, this is J3, J4, and J5 will be minus C1 S234 minus S1 S234 minus C234. So, if you look at T05, okay, T05 is not given here, but if you look at our previous derivation of the forward kinematics, you will see T05 had this, the rotation matrix had the approach vector as this. So, that approach vector is coming here as J5Q. Now, you have the JQ, full JQ as J1, J2, J3, J4, J5. So, these are the columns J1, J2, J3, J4 and J5. So, you have the complete Jacobian identified. Now, again you can see the Jacobian is a function of the joint angles. So, this way we can get the both the linear velocity part and angular velocity part of the Jacobian. So, the linear velocity part is you take the derivative, partial derivative of the position with respect to theta 4 or theta 5, you will be getting the linear velocity part. I hope you understood how do you get the Jacobian. So, the top part or the linear part is the same as what we did, and it is applicable to the previous Jacobian discussion what we had also, but the angular velocity part is the one which we are actually seeing as new one here, and the angular velocity is basically that angular velocity part depends on the orientation of the joint axis. So, that is what you need to understand from conceptually. The conceptually what we are trying to say is that the angular velocity of this frame, so angular velocity of the tool tip depends on the orientation of the joint axis. So, if the joint axis is in this orientation and we make a rotation about this joint axis, then the angular velocity will change here depending on how this axis is oriented with respect to the base axis, base frame. So, the orientation of the joint axis with respect to the base frame decides the angular velocity of the tool tip, and therefore, we take that as the bk here and then write okay, this relationship, this orientation of the joint axis is the one which actually determines the angular velocity. So, any change in this angle will affect the velocity here, and as a function of how this orientation is there, how these two axes are oriented, that is the way how you get it. Okay. So, that is what how we calculate the the Jacobian for a manipulator. Okay, so we saw this calculation of Jacobian, and always we see that we need to do a partial differentiation to get the linear velocity part of the Jacobian, and that may not be always feasible. So, we have to manually do the partial differentiation and then write it, but there is a numerical way of doing this, a numerical computation of Jacobian. So, instead of going for the partial derivative and then finding out the Jacobian, we can have a numerical computation of Jacobian. So, we will see how the Jacobian can be computed numerically. Now, look at the manipulator shown here. So, you have a manipulator shown here. So, this is the manipulator. Now, we want to find out, suppose this is the manipulator and these are the joint axes that you can see, these are the joint axes. Now, we can see that the Jacobian can be calculated as the cross product of the joint axis vector and the position vector of the joint to an nth vector. Okay. So, now what it says that if I want to find out the velocity at these points, then I can find out the vector here, this is the joint axis vector, and a cross product of this vector with the position vector, this position vector will give me the velocity relationship. So, that is what actually says the cross product of the joint axis. So, this is the joint axis, and at this axis when I rotate with respect to this axis, this will be changing, the tip will be changing, the position will be changing, and the change in velocity can be obtained as a cross product of the joint axis and the position vector which connects the tool tip to the joint, that actually decides the velocity of the tip. So, that is what actually it says, can be calculated as the cross product of the joint axis vector and the position vector of the joint. Similarly, we want to find out what is the effect of this joint on the velocity of the tool tip. We can get it by looking at the axis of this and taking the cross product of this joint axis with respect to and cross product of this joint axis and the position vector. So, this is the position vector from this joint to the tool tip. So, you can take the cross product of this with this, you will be getting the velocity. So, that is what actually the principle of numerical computation. So, you get this j as j1, j2, j3 etc., and then j1 the linear part will be this and the angular part will be this. So, the linear part can be obtained as b I minus 1 cross p n 0 p 0 n minus p 0 I minus 1. So, this actually represents the position vector from the joint to the tool tip. Okay. So, n 0 is from 0 to n, and 0 to I minus 1 is from, if this you are talking from this point. So, from here to here what is the position vector? What is the position vector from this joint to this joint is given by this. So, p n to 0 is the position vector from base to the tool tip, and 0 to I minus 1 is from the base to the joint from which we are, for which we are calculating the velocity relationship. That gives the position vector from n I minus 1 to the tool tip. So, this gives you the position vector and this gives you the joint axis I minus 1. So, the cross product of the joint axis to the with the position vector gives you the velocities. That is what actually given here, b I minus 1 cross p n 0 minus p 0 I minus 1. Okay. That gives you the linear velocity part, and then the angular velocity part we already saw I minus 1. So, b k we said. So, we will be able to get this as b I minus 1. So, b I minus 1 is 0 to I 0 0 1 transpose. This is the same thing what we discussed in the previous case also, that is the joint axis vector. So, b I minus 1 is the joint axis vector. Okay, so, what we need to do is to take the cross product of I minus 1 with respect to the position vector. So, take a simple example of here for a 3 degree of freedom manipulator. Okay. So, for a 3 degree of freedom manipulator, J1 will be B0 cross P30. So, suppose this is a 3 degree of freedom manipulator, I consider this as a 3 degree of freedom manipulator. Now, what it is saying that J1, the first column of the Jacobian, will be B0 cross P03, that is this is B0, that is the first joint axis B0, that is the joint axis, cross this position vector, okay, that is P30. So, P30 says that the 0 to 3, that is the vector representing the 0th joint to the 3rd joint, that is P03, and B0 is the joint vector, and B0 is obtained by the from the rotation matrix. The approach vector of the rotation matrix will be the B0, and then J2 will be B1. So, B1 is the this joint axis. So, B1 cross this position vector, okay, P30 P03 minus P01. So, P03 is this one and P01 is this one. So, the subtracting that you will get this as P13. So, P13 will be the position vector of 1 to 3. So, you will be getting by okay. So, P03 minus P01 is the position vector, this one, and this one the B1 is the joint axis. So, B1 is obtained from R01. So, now you take the rotation matrix from 0 to 1 and then find out the approach vector that gives the orientation of this axis with respect to the base frame, that becomes the R1, I mean that becomes the B1. So, B1 will be the angular velocity part, and B1 cross P03 minus P01 will be the linear part. So, this way you will be able to get the compute the Jacobian numerically. So, now you do not need to do the partial differentiation, take the cross product and get the values using these methods. So, that is the way how you get the numerical computation of Jacobian. Okay, so, this is an exercise for you, homework. So, write a program for numerical computation of Jacobian for an n degree of freedom manipulator. So, you can actually calculate, I mean now you know the numerical methods. So, you can write a program to find out the Jacobian matrix, because you already written a program for the forward kinematics. So, you can actually use the same program to get this T01, T02 etc., and from there you can actually get P0n, P01, P02 etc. you can get, and once you have that you will be able to get the position vector, and from the rotation part you will be able to get the B matrix, B vector, and then do the cross product and then get the Jacobian. So, you can write a code, you can use C or Python or whatever the language you like, and then write a program for calculation of Jacobian. Okay, so, that is about the computation of Jacobian. So, we discussed about the importance of Jacobian and how is it used for controlling the robot manipulator using the Jacobian inverse to get the joint velocities, and then we saw how to compute the Jacobian analytically as well as in numerical methods. Okay. Now, we will just see how to use this one for static analysis. So, we found that the robot joint torques and the forces also need to be computed, and the relationship between the robot joint torques and the forces and moments at the robot end effector is basically the static analysis. So, suppose you apply a force here or apply a moment or a force here, we want to know what is the torque to be acted upon these joints to balance that one. Or if you want to apply a force on the environment using the manipulator, or I mean in a static condition, what should be the torque to be applied to apply that force. So, this is the static relationship, or you are actually holding a weight here. So, the robot is asked to hold a weight in a static condition. We want to know what should be the torque needed to withstand the load acting at the tool tip. That is the static analysis, and this we can actually use using the solve using the Jacobian. So, the manipulator Jacobian is defined as a relation between the infinitesimal displacement to the joint displacement. So, the same thing applied, that if you have a infinitesimal displacement at this point, that will lead to an infinitesimal displacement at this joint, and that actually can be overcome by a can be compensated by a torque applied at joint to reduce the movement of the joint. Okay. So, that is the way how you use the Jacobian to analyze the static forces. So, we can actually write this as, so if the joint torques are given as tau and the forces and moments acting at the tool tip is given by F. So, if this is the force and moment acting at the tool tip, then the joint torques tau 1, tau 2 and tau 3 can be obtained as tau is equal to J transpose F. So, that is the relationship, tau is equal to J transpose F, where F is the forces and moment and J is the manipulator Jacobian. Now, if you know the forces acting, the forces and moments Fx, Fy, Fz and Mx, My, Mz, the 3 moments and 3 forces, then we will be able to find out what is the torque acting at the joint based on this relationship, tau is J transpose F. So, this is the relationship that we will be using in order to get to do the static analysis, and J is the Jacobian of the manipulator. Okay. So, you can write this as tau 1, tau 2, tau n, depending on the number of joints, you have n joints. So, you will be having the joint torques 1 to n, it is an n by 1 vector, and this is an n by 6 Jacobian, and then this will be a 6 by 1 vector Fx, Fy, Fz, Mx, My, Mz, and the transpose of the Jacobian will be used for getting this one. Okay. And the transpose will be the n by 6 matrix. Okay, so that is the way how you do the the static analysis. Okay, so here also there will be some singularity situations, because we have a tau is equal to J transpose F, but now here the singularity is that the rank of J transpose T is equal to the rank of J theta, and that singular configuration there exists a non-trivial force F such that J transpose F is equal to 0. Okay, there may be a situation when J transpose F is equal to 0, that is your the forces the torque at the point will be 0 for any force acting at the joint, any force acting at the end effector, or the other way also any torque applied cannot produce a force at the end effector. That kind of situation is known as a singularity, force singularity. In other words, a finite force can be applied at the end effector that produces no torque at the robot's joints, and this is known as the robot lockup. That is, you can apply a force. So, suppose the manipulator is like this and apply a force here, a force is applied here, no torque is generated at the joint. So, that kind of a situation is known as the force singularities, or the singular configuration in the manipulator, and this situation is known as a force lockup, or they call it as it is a lockup condition where the torque at the joints are 0, and this can actually happen in many situations, especially when it is in a fully extended position or a boundary singularity conditions, you will be able to see that such situation happen. So, let us look at a case where actually this can be shown. Assume that the force acting at the end effector is given as, okay, this is the manipulator, a planar manipulator is considered, where this is at the theta 1 position, the joint 1, and joint 2, joint 3 are 0 angle, and you apply a force F here. So, you apply a force F here, and its components are Fc1 and Fs1. So, the components in x and y direction can be written as F cos theta 1 and F sin theta 1. So, that is the force. Now, there is no moment acting at this stage, we assume that there is no moment acting. Now, so theta 1 is theta and theta 2, theta 3 are zeros, a planar 3R manipulator. Now, for this tau 0 can be written as J transpose F 0. So, we have tau, that is the joint vector, joint torque vector tau 0 is J transpose theta F 0. So, this will be the relation that you can get, this is the F 0. So, this is the J transpose F and F 0. Now, we can see that this is equal to 0 for the condition where the sorry this will be 0. So, this will be 0 because minus Fs1 C1 L1 plus L2 plus S3 plus Fs1 C1 L1 plus L2 plus L3. So, this is 0 and this is 0 and this is 0. So, you will see that the tau 0 is 0, that means no torque is acting at these joints because of the force. Now, it is very obvious from here because these are aligned or these aligned, and then any force in this direction is not going to produce any torque in the manipulator or any torque in the joints, because the force is always in this direction and therefore, no torque will be acting on this to overcome this force. That force is not really reflected onto the joints, and this is the situation known as the lockup or the singular force singularity. So, that is another situation that will be encountered in the manipulator when this in the singular configuration. So, you can see that is actually a boundary singularity also. So, it is actually coming out of the boundary singularity of this particular manipulator. Alright, so that is all about the Jacobian. So, we will stop here the discussion. In the last few classes we discussed about the Jacobian, the inverse kinematics, then we talked about the tool configuration, joint space velocity, and we talked about the Jacobian. So, the how the tool configuration velocity and joint space velocity are related using the Jacobian, and then we looked at the singularity issues, the boundary singularity and the interior singularity, and finally, we talked about the generalized inverse as well as the pseudo inverse and statics. Okay, so, we completed the discussion on the kinematics here. So, we started with the basic mathematical foundations for representing the points and objects in space, and then we talked about how this the position and change of position can be represented using transformation matrices, and if you have to represent both translation and rotation, we found that we cannot use a 3 by 3 matrix, we have to go for a higher dimension space, and then we defined the homogeneous coordinates and homogeneous transformation matrices. And after going through the physical elements of industrial manipulator, the type of joints and the type of configuration, we started the kinematic analysis, and we talked about forward kinematics, how the position of the end effector can be related to the joints, and then we moved to the inverse kinematics, where if we know the position of the end effector, how can we find out the joint positions or the joint parameters. And while developing this, we talked about the DH parameters and arm matrix, and after discussing the inverse kinematics, we moved to the differential kinematics. We found out the relationship between the joint velocities and the end effector velocities. So, this relationship can be represented using the Jacobian matrix, and then we saw how the Jacobian matrix can be computed for industrial manipulators for the linear velocity part and angular velocity. And finally, we discussed how the Jacobian can be used for static analysis. Okay, so with this I am completing the discussion on manipulator kinematics. From the next class onwards, we will be having lectures by other faculty members. I hope you enjoyed these lectures, and wish you all the best. Thank you.